All right, well, welcome. This is a interview with Mayalen Etcheverry, who is going to be giving an invited talk at the Cells to Societies workshop at ICLR. Mayalen is a second-year PhD student at INRIA with the Flowers Group, if I have that right.
Yes.
And uh, the topic of the research involves things like curious AI, open-endedness, metadiversity search, and automated goal generation, intrinsic motivation sorts of things. So I'm curious, you talk about the potential for open-endedness in your workshop abstract. Do you want to sort of say what sort of things you intend by that, or where you see that happening?
Yeah, sure. So, well, first, thank you for inviting me to this workshop. And yeah, so when I'm talking of an open-ended system, in general, we mean a system whose behavior is not convergent over time. So it's a system which keeps surprising you and producing new and interesting outcomes. And so from our computer scientist perspective, like if we were able to design, come up with a computer program or an AI that would fit this description, well, I guess it would be very desirable, of course, across many practical domains. And one sort of open-endedness that I'm really interested in my work, and for which I believe that AI can play a big role, is with respect to our scientific discovery practice in complex systems. So, there are many complex systems that are studied by scientists at the bench. Chemists are trying to discover new drugs or new materials. Biologists are trying to bioengineer these like functional tissues or organs. And then you have also computer scientists who are like our people who are exploring even numerical complex systems like models of cellular automata, for instance, to inform about theories about the origin of life or intelligence. And so why I'm talking about complex systems is because I think that they are great candidates for open-endedness in the sense that they kind of offer us already this unbounded possibilities for emergence. And so, but at the same time, they're very hard to explore and to navigate for us humans. So I always take this example of the game of life, which I think is a good example. So it's a very simple numerical system where we fully know the rules. It's fully deterministic, and still, like, it has been created more than 50 years ago, but players are still discovering new and increasingly complex patterns in it by, I don't know, running it for hours, for instance, on supercomputers. And so it's a good example of how our discovery practice is really difficult in the system. And I think that the same holds, like, for the same trend holds for chemical and synthetic biology system. There is even like this sort of trend or law, which is I think interesting. It's like I think it's the reverse of Moore's law. So like even though we are getting we have this exponential increase, in technology and resource and compute, so we are getting better and better and doing chemical tests and running them massively and in parallel. But paradoxically, instead of having like exponential increase or like making discovery much faster and cheaper, it's actually much slower and much harder. So that's, I think, a very interesting tendency. And you could even say that kind of as a society, we're maybe starting to converge. That's a bit extreme. And I'm not saying like, that scientific discovery is not open-ended, but I think that maybe we are reaching a point where the range of problems, of scientific challenges that we are trying to tackle are so complex that we really need new tools to help us tackle them and kind of to avoid this convergence point and unlock all sorts of new possibilities. So I think that's what I mean when I mention like open-ended discovery in the system. I really hope to kind of unlock possibilities for discovery in complex systems.
Yeah, so you had some recent work with Lenia, where you were able to use this sort of method to discover all sorts of behaviors that would be quite hard to hand design.
Exactly. So we have working mainly on numerical systems so far, especially linear. Yeah. And we, exactly, so we, in our latest work, we were able, like, with machine learning tools to discover new forms of self-organized agency. So it really looked like some small life forms that were moving around in cellular automata. And that's something that has been really hard to find by hand, also by random exploration or by optimization methods. So it's really not an easy problem.
I wonder if I should show some of the videos from your recent work. I guess we can include a link.
Yeah.
So one of the things I'm kind of curious about with regards to open-endedness is, like, a lot of the examples you gave, you have a kind of a purpose in mind, like drug discovery. There's a sort of demand on the human side of what we want that to find, but at the same time, for the system, there's something, I guess, more innate to the system that it wants to discover, some way that it's going to have the most success following, or even things where it has to do something we wouldn't know is important in order to get to interesting states. Do you find any kind of tension between those things in your work, or do you have any way of resolving that?
Sure. So indeed, like, there is this problem that, especially when we are doing machine learning programs, at the moment we are, we tend to strongly define, like, the task that we want our system to be solving. So we are trying to, at the same time, like, get away from this too strong task specification that you do typically in optimization, where you only define, like, for instance, this scalar reward, and you want your system to, converge to the peak in this fitness landscape. So we have proposed in, like, previous work some ways to a bit escape this strong constraint. But at the same time, as you said, like, we just don't want the system to go randomly and do things that are not interesting for us, because at the end, we are, as humans, we are evaluating the discoveries. And so we want something that fits our preferences. So it's kind of this, this not easy to manage balance where humans have preferences, but at the same time, they don't know how to how to define them, how to make a computer quantity out of it. And so we, in previous paper, for instance, this metadiversity paper, we have kind of this interactive things where the agent should boldly explore the space, but at the same time, like, show its discovery, for instance, periodically to a human, and then the human could give some feedback to, guide back the exploration.
So you mentioned metadiversity, and there's a bunch of stuff that's sort of, I guess, flat diversity, quality diversity, where it's just trying to explore the space. But with this metadiversity idea, do you want to explain that? Like, what sort of the difference is between that and the sort of the novelty search stuff?
Yep, sure. So this metadiversity idea, it's something that, we've came up when we were, trying in practice to formulate exactly this problem of making an open-ended form of discovery as systems in complex systems. And so, as you mentioned, like, the kind of the first idea or first family of machine learning algorithm that came to our mind was more like this novelty search types of algorithms, because so it's this family of algorithms that come from, evolutionary or developmental robotics, and that seems to be a good fit with respect to this optimization methods, because instead of trying to optimize the fitness, it would try to optimize the novelty of the discovery. But so we started with that, but then quite a critical part, and it's a well-known critical part, is that they still assume, at least in their standard definition, they still assume, like, this, that you have some sort of oracle representation, so that will basically, from your system raw observation, it will describe the interesting degrees of behavioral variation in your outcome. So I like to see this representation as kind of taking a lens on the system. It's like putting a pair of glass and only looking at these few factors of variation that can emerge in your system, and then trying to find the novelty and diversity within that lens. And so I guess the family makes sense, or we're more successful for simpler physical systems like robotics. We have some experiments in the flowers team where, for instance, you would put a torso robot with an arm that it would be on a table and it could manipulate, for instance, a discrete set of objects in the room. And so here it makes sense, to look at, instead of looking at the raw image, you could look only at the position of the object. And then if you would find novelty in this behavioral space, it meant that your robot would learn, to grasp objects and move them around. So it would make sense to look at this only through this lens of the system. But in complex systems like Lenya, where we have this raw video of pixels, there is no one unique lens that you should use. I think there is like tons of lenses that you could use to describe the system. And so it's not trivial first to define one lens, and not trivial also to know the impact that using this lens will have on your flat novelty search like discoveries. So actually to test that, we did this. We had this interesting experiment where we tried to run the same equivalent of novelty search algorithm, but with different lens. So one lens was, for instance, undefined with statistics from the original Lenya paper. Or we have one lens, we would use, for instance, Fourier descriptors. Then we also used unsupervised learned lens. So, for instance, you would pre-train a VIA on a big, database of Lenya patterns. And we even tried a VIA was trained online, so the lens will not be so static anymore, but it will be fixed in capacity. And so we ran the algorithm, and we have this interesting kind of two striking results coming out, that if you run algorithm using lens A and like you project it in the space of lens A, indeed it's going to be very diverse, your set of final discoveries. So it shows that novelty search is very, I think, efficient at finding new solutions, at least in systems like Lenya, but in a given state space. But if you take the same discoveries and project them through lens B, then they would achieve a very poor diversity, because all the degrees of variation that make them diverse in space A will kind of disappear. So here it will be kind of miss potentially other types of interesting types of diversity. And so that was kind of the point of this novelty search experiment. And so then kind of the meta diversity came very naturally, as this idea that either your open-ended system should not try to find new solution within its existing state space or view of the system, but it should continuously try to extend and try to incorporate other degrees of variation that could emerge in the system. And so that was kind of the intuitive idea behind metadiversity. And then in this paper, we formulated it as some sort of bi-level exploration loop, where you have an agent in an outer loop who is trying to learn divergent feature spaces and extend this like a module of like a set of modules of feature space to characterize the system, which would be the lens. And then in an inner loop, you will run some equivalent of novelty search in each of those spaces. And also something that we emphasize as very important, as you said, is to put some human in the loop, to kind of prioritize the state space that for the human were interesting. So that's how we formulated metadiversity.
So the relationship between the levels, I mean, it's like, if I imagine, let's say you just took every single pixel, you'd have this huge dimensional space, and you would never really fill it, or like everything would be diverse automatically, because everything would be different in some pixels, and they wouldn't necessarily be meaningful differences. But when you construct this space hierarchically, do you find that the kind of lenses you get are special in some way you wouldn't have been able to get if you tried to jump straight to them? Like, do the lenses themselves tell you something about the system?
So I guess that yeah, so first of all, you cannot, you could say, yeah, why not try exploring right away the huge dimensional space of Excel? But that's known to be not efficient for multi-search types of algorithms. So you need lower dimensional spaces. And then, so indeed, in this paper, we built them hierarchically, but there was, I guess, one possible implementation of metadiversity search, at least of this idea. I guess there are many other ways that you could do so, but the intuition about doing it hierarchically was that, first, you don't know anything about the system. So you want actually some kind of VAE, like some coarse compression of it that would, right away give you the main factors of variation, like maybe, I don't know, average intensity, like the coarse form of the pattern or something like that. And then you probably want to cluster your discoveries to kind of start like separating them, into niches that seems to be more related between them. And then you want to instantiate a new lens per niche, kind of like, so probably you will have this niche of texture looking patterns with very high frequencies, and here you want to not have just a coarse description, but you want to go more in details and start seeing that you have some zebra patterns or wave-like patterns, and then again you want to cluster them and instantiate new lens. You kind of have this coarse-grained view that seems meaningful, but there are maybe other ways that you could construct those lenses progressively.
So it's like in each niche, you're trying to find the thing about that niche that kind of wants to vary, and then you just ask it to like vary more or to vary more completely.
Yeah, that's it.
Do you think that this kind of resolves the, the kind of, I don't know, the lazy way that a lot of intrinsic motivated systems will just sort of fill up entropy from the bottom, because you're sort of saying, here's a direction that you already want to vary and you can explore this, but I'm not going to give you like, every direction. It's going to be, the top 2 directions at a time. And then when those are done, you have to find another split before you get to have another direction of entropy to fill up or something like that.
That's a good question. So I guess it depends on the system. In Lenya, as I told you, we had this very strong result that generating diversity in some direction was not driving diversity along other dimensions. For instance, we had a very striking example where we use these Fourier descriptors. We were characterizing, frequencies in the image, and at the end of the exploration, we would only have discoveries in Lenya that were purely vertical stripes. So that was interesting. So kind of the intrinsic motivated system has exploited the fact that you're searching for diverse frequencies, but it would only show you vertical stripes. So indeed, with all kinds of frequencies, but intuitively, it's not what you expect of diversity. Like, even though it found all kinds of frequencies, you wanted to have some other types, like wavy forms or localized patterns, like that. So you could say it's some sort of lazy, indeed, problem of intrinsic motivated system. And then once again, it shows the importance of having good, good goal spaces, good way to characterize the system.
Yeah. So, like, along those lines, do you have some idea now? Could you say, like, is there a standard by which you could say this is a good goal for a system to have, this is a bad goal for a system to have? Is there some kind of objective measure, or is it really all, or does it really have to be constructed sort of from within the system's point of view?
So this kind of, what is a good goal? So once you're in this task space that you define, I guess, so at least in the Flower team, we are working a lot, in this intrinsically motivated goal setting system. And we generally say that good goal should be along kind of this 2 dimension. First, as we discussed, a good goal should be novel and interesting. So it should be like in this kind of creative goal. And the other dimension is that it should be feasible. It should be learnable. So it should not be too easy or too hard. And so personally in my work, I've used, very basic strategies for all of these dimensions. So for the novelty, I was just like uniformly sampling in the goal space with the intuition that if you manage to uniformly cover the space, then you should reach maximum diversity. Then for the interesting part, well, as I said, we use kind of this basic scoring system where you would have some human that could, score the state that he believes interesting, and so you would prioritize goal sampling in those spaces. And for the feasible part, we either didn't implement. I mean, in my work either didn't implement any smart thing, or just in our latest work that you mentioned at the beginning, we have this basic curriculum ID where we sample goals, not too far from the set of goals that we have already reached. But there are, for those 3 dimensions, there are many other and more advanced strategies that have been proposed, especially in the Flores team. So for novelty, you could use kind of count-based estimation, or you could train some generative model distribution and try to sample, inversely proportional to the probability of sampling in that distribution. For interesting, we have also, there are my colleagues in my team that are trying to incorporate language in the goal sampling strategy. So like human could communicate somehow goals. That would be very cool. And for the curriculum, you have also more advanced strategy of automatic curriculum learning, where, for instance, there is this idea of learning progress. So you should, you can empirically estimate how good you are doing in, across different goal regions, and then you would sample toward these goals of intermediate difficulty that are not too easy or not too hard.
All right, well, great. Well, thank you for your answers and for giving us the time to have this interview, and I look forward to your talk.
Thank you, Nicolas.
All right.
It's a pleasure.